Thank you for attending. This is the first full session that we've ever done with Pandas and using the Spatial Enabled DataFrame. And I'm Andrew Chimkowski. I'm a developer on the Python API team, and I developed the Spatially Enabled DataFrame. So just for some background information for those who don't know, the ArcGIS API for Python is a Python library used for managing your WebGIS. It has both local and web-based capabilities, and you can do geo-enrichment or access things like geometry and geocoding. You can use geoanalytics and even just regular feature analysis. It really all starts with your GIS and connecting through there. But the nice thing about leveraging Pandas in the Spatially Enabled DataFrame is that you don't actually have to connect to your GIS in that. So this is where the conversation kind of diverges from what's traditionally known, what you see in a lot of the other demos or when you use it. So you can use this completely local and disconnected. One of the nice things about using the Python API and Jupyter is that they work very well together. You can take advantage of the full visual representation of information and the mapping that we have, and you can bring it all together to do really robust analysis. But we're going to start from the very basics for those who don't know. I just want to get a feel of who works with Pandas on a day-to-day basis, or right, that's great. Who's just used it once in a while, maybe starting to play with it, just so I know? Great. That's even better. Well, welcome to the world of Pandas. It's a wonderful, wonderful thing. And who has no experience at all? Even better. Okay, so we're gonna start from the ground up. We're not going to be able to cover all the basics of Pandas, but I'm going to try to hit on some of the main issues. And I'm going to build it up from there, and we're going to go. And we're going to basically step through this workflow where we're going to introduce Pandas, show how we can use Pandas to clean up data and do analysis and visualization. Then we're going to walk into the spatial side of it, and we're going to talk about all the functionality of the Spatially Enabled DataFrame. And then we're going to bring it all together in one big use case at the end and bring in everything we learned from before. So we're going to start it with, what is Pandas? Thank you. Pandas is a package that provides flexibility and an expressive data structure, and it's great, and it makes your data labeled, and it's pretty, and the Pandas people actually describe it, and they strive to make it easy and intuitive. If you want to relate it to a product that most of you have probably used over your lifetime, that's Microsoft Excel. Think of it as an Excel, but really more responsive if you were to visualize it. Then it comes to, okay, why use Pandas at all? And Pandas has a lot of points and a lot of reasons to do it, but I want to hit on some of the main issues. It works really well for working with missing data, so it's easy to take out information that rows and columns that don't have the information, so it doesn't muck up your analysis as you go through. It's mutable, so you can add records, delete them, and change it as needed, both on the column level and on the row level. It has the ability to group data by logically, and it has great data alignment. So if you're doing operations on two different data frames, Pandas will try to line your information up for you so it matches up. Some other reasons is that it uses labeling and slicing. So if you're familiar with Python arrays, you can do the same sort of slicing on your data frames and series, which as well. And you can even reshape and pivot your data. So let's get started. So it all starts with an import. So import Pandas as PD, and that imports the library. And as programmers, you don't want to write Pandas every time. So we say, I don't want to call it Pandas anymore. I want to call it PD because I don't want to type as much as I have to. Lazy programmers. The next thing, if you're going to do any plotting in Jupyter Notebooks, and this is only specific to Jupyter Notebooks, you should do the magic function %matplotlib inline. And this allows graphics to actually show within Jupyter Notebook. So we're going to start with a series, and all a series is a one-dimensional array, and it can hold any data type. You can create a series by passing in do pd.series and pass in some data. You can even specify a customized index. So what do I mean with that? So we're going to use numpys and generate just some random integers. And we're going to load in some information here. So I have some code that I'm loading up, and I'm going to instantiate my series by passing in this random data. What you notice is that this series, this one-dimensional object, actually has two columns when you look at it. On the left, it has an index value that you can reference your data by, and on the right is actually the data itself. Series also have data types, so you know the information that you're working with when you work with them. So building up from that one-dimensional array, and if we put them together, we can start building data frames. And this is that Excel spreadsheet example. This is your two-dimensional array, so you have both an X and Y. So you have your columns going out on the X-axis and rows going down on the Y. And it feels like an Excel spreadsheet. So you have your column headers, then you have your data that goes across in rows, and information in columns going straight down. Now, it doesn't have to be one data type in a column. It can be mixed. It can be everything. So I could have one column that has a date time. It has an object. It has a float, an integer, all that information. It's not picky with what it is. So it gives you the flexibility to put your data the way you need it. And we can go ahead and do an example with that. So I'm going to take an array. I'm going to take a list, and I'm going to create a list of lists. And I'm going to specify some field names. And these are just dummy information. It could be any value. I'm going to load in some code, and I'm going to create that data frame. So we do pd.dataframe, and we pass in our data and the column fields that we want. And if we go ahead and print that out, we get this two-dimensional structure that we talked about. So we have our columns on the top, our column names, and then we have each row. And notice once again that we have the index on the left. And right now we're just using default indexing, and we'll get into that a little more. But now that we know how to create the data frames from nothing, let's see how we can leverage some of the other functionality to build out and get the information that we need as we go along. So if you've done any examples on the internet, there's a data set called iris, and this has to do with length and width of irises and flowers. So you have the length of petal length and things like that. And really what it is, it's just trivial data that will help talk about how to do the functionality. So what we have here is we have our data frame, and we peeked at the data. And what peeking means is basically we take a sample either from the top or the bottom, and we're going to look at the first 5 rows or the bottom 5 rows. And those are the default values. And it gives you an idea of what is contained in each column without loading the whole data set and maybe clobbering your system. We can go ahead and we can slice that data frame and get pieces of it that we need. So we can step by 3s, we can step by 1s, which is the default, just like you would if you were to step through a list in Python. So here we're going to start at row 23 and end at row 31 and go every 3rd row and print it out. We can also describe the data set. And what describe is going to allow us to do is it's going to give us a sense of what we have, especially numerical data. And it's going to print out things like the standard deviation, the min and max of all the columns. And so now you can look at your data and see how it's distributed. If you do anything with sampling, you can shuffle your data set. A lot of times you can load information in from databases, and it comes in pre-sorted. So when you're doing random sampling, often that can create biases in your data. So it's nice to sort of shuffle it up and mix it up just like a deck of cards. When you open up a new one, everything's in order. But when you shuffle it up, you get a better distribution to all the other players of your game. So we're going to do that with our data as well. So we're going to shuffle it up using the sample function. And because we don't want to know what our prior index was and how it was shuffled, because if we're going to go on and do sampling again, we're going to reset that index. So we don't know how it shuffled it up because we don't care about that. And then we can peek at our data set again. And if I were to run it again, you would get a different result every time, and the data would just keep getting shuffled up. And you can do that 1 to n times, so however many times you want to do it. Often when you load data, you want to know what your columns are, just the names, so you can access them. So df.columns gives you a list-like object with all your column names. And you can walk over that just like you would an array. So if you want to go column by column and analyze your data, you could do that. So you could use a simple for loop. So you could go for field in df.columns and get the field name and query those data sets. We can also look at the D types or the data types. So when you load data, everything's associated with the data type. If it's a single data type in there, in the column, it'll try to figure out what it is. So my first 4 columns in my data frame are all float 64s. But notice name, which is a string, comes back as objects. So when you look at name, or any column that's a string, it'll always come back as an object. That's how Pandas handles that. And that can throw people off in the beginning. Next, we're going to access information and talk about that. So accessing information is a zero-based indexing like most data structures in Python. And you can use it using the lock functions. So think of them as locations. And iLock means we're going to reference it by index. And location, usually you're locating it by some other object. So you have a datetime object, but we're going to show that later. And we're going to use the bracket notation with the column name to access information in specific columns. So if we want to access data for a single row, we're going to use iLock and then put the index value that we want in there. And this returns back a single row, and that sort of acts like a dictionary. So we can access it by name that we want. So let's say we wanted the length here, and we could just get that information out. We can select columns using that bracket notation, and you can select one or many. Here we're going to select 2 columns and then print out the first 5 records. So now we're creating a view of our data set in memory and just displaying what we need to show. To get at single values, we're going to use the iLock again on our series this time, name, and we're going to print out the first row. We showed some slicing earlier, but the syntax goes like this. So using iLocation or index location, you can also slice, and the syntax goes like this. We have our start index, and then we have our stop index, so our starting and stopping point, and then the step size that we want to do. So we can do df.ilock and do 1 through 16, and in this case, I'm taking every 3rd record, starting at 1. I could change that to 4 and get a different result. And notice, the one thing you notice is that it doesn't include the 16th row, even if it was 4 from the previous one. So if I made that set, it won't include the last row in there. So you just be cognizant of that. Some best practices when you work with Pandas is one's called method chaining. And this is where you call multiple functions at once in order to prevent multiple calls on your data set. So when you have 100 or 200 rows, that's not really anything. But when you have 1 million, 2 million rows and you're working with it and you want to make manipulations on your data set, you don't want to constantly walk over the information to do operations. So you want to do it in one shot. So here's an example. I'm going to take my data frame here that we've been working with, and I'm going to rename all the columns, and I'm going to set them to lowercase. Then I'm going to walk my data, and I'm going to take all values using lambda functions in the name series and make those values lowercase, and then print out the results. So you can see how we changed our data frame and by chaining all the methods, and we only did it in one walk instead of multiple walks. So it improves performance. Often we have time series data, and one of the benefits of Pandas is that it works really well with datetime values. PD.2 datetime will actually try to infer datetime information, and you can pass it in multiple ways. So if we take this data frame here, we're going to have datetime values spread across multiple columns. So I have month, day, year for each of these columns, and that's what this list of lists represents for these 3 records. And when we print it out, each one represents a part of the date. We can go in and we can use this toDatetime, and based on the column names, it'll be intuitive enough to add a whole datetime column and put it out there. I didn't have to tell it the datetime format that it was in. It just knew by those common names that this is now a datetime value. Here we're going to take the data set again. I'm just going to rebuild it. And what we're going to do is we're going to set that datetime value of just month, day, and year, and we're going to set it as our index, and then use the location function to get the single row. So we took the 3 columns we were interested in and created a series. Then we assigned that series to our index, and then we got the row. So that's what happened in these couple lines of code. Next, I want to talk about categorical data. And what categorical data is taking string information that may repeat multiple times in your data set and associating it with an integer. So think of it like domain values in a feature class, because that's a good association. And the reason you would want to do that is for large data sets, string data can take up lots of space in memory, and integers take up little bit of information. So you can manage your memory if you have long descriptive strings that are constantly repeating, and put it and just replace them on the back end. That information is just associated to a 0, a 1, a 2 value for every piece of labeled information. So what we're going to do here is we're going to create a random data frame, and we're going to generate some labels that'll do the range. If you know you have labeled data from the get-go, we can use pd.cut to assign those labels, and it'll figure out every label for that categorical data in one fell swoop, walking over the data. And here's an example of that. So our group, we have this value 91, and here's our grouping 90 to 99 and 13, so on and so forth. And even though it looks like a string when it prints out, on the back end, it's just an integer value that points to a mapping table on the back end of Pandas. And if we were to look at the data type, you see that instead of, it doesn't say it's an int like our data is, but it's actually a category data set. We can also, on reading of data, we can declare a data type. So in this case, I have a data set that's about drinks from around the world and how much people drink in each country and various continents. And one of the columns I know that's in this CSV that I'm pulling in, it's called continent, and it repeats multiple times. So I can use the pandas.read CSV file to consume this information. So not only from a local file, also from a URL. And I can declare my data types on load. That way, once again, we're not walking the data multiple times. So the theme here is you want to walk your data as little as possible and only do it when you have to do analysis. So it's very important. So we're going after we do the read, we can then print out each category, and we have each unique category for our continents that the data applies to. We can also do the as types after data is loaded. So sometimes you get CSV files and you don't know what you have in it, and that happens a lot. A lot of the information that you consume when you're doing this type of work is sort of just discovering what you have to begin with. So once we read in our drinks data set, we can do an as type as once, but instead of doing as types for each individual column one time, we can pass in a dictionary with the column names that we want and declare the type that we need. So it's going to cast all these values from whatever they were before to floats for all the beer servings. And then for spirit servings, it's going to cast them to floats as well. And then we're still doing our continent and making that a category. We can do aggregations and multiple aggregations at once. So they can be done first on a series. So we have our drinks data frame, and we're going to take an individual column called beer servings, and we're going to aggregate the mean, min, and max for that column. So the average amount of beer is 106. The min, some places don't drink at all, and the max is 376 million gallons. We can also do it on the data frame as a whole. So you can do aggregations on every column without declaring it, or you can specify what you want to do. And what we have here is we have the mean, min, and max. And the one thing that's kind of interesting, notice that country, you get a min and max. That's because the first letter in the alphabet is A and the last one's Z. So you get min and max, we'll come back with that. But mean doesn't make any sense for string data. We can group our data. In this case, we're going to group it by continent, so our category. And then we can calculate the mean, min, and max again, and other statistics for that specific column, but it's grouped. So for Africa, we can get the mean, min, and max. For the EU, and so on and so forth. So we can aggregate that, and grouping by is an intelligent way of taking your information and pushing it together. We can then go ahead and visualize some of our data. Oh, disappeared. There we go. And we can take our data frame, and there's a plot function. And the default plot function, if you just give it an XY column where the information is coming on, is just a line graph. But you can be very advanced with your visualizations that you can do for the plot functions. You can make these binning hexagon plots, and there's a whole host of other visualizations you can do. And it integrates well with other libraries. So you can bring in Seaborn or Plotly and all this other stuff to really make some really cool visualizations. So now that we've learned about some of the basics, let's try to put it all together and do some data wrangling through a demo. So we're going to use Pandas, and we're going to try to cleanse the data that we're going to pull in, and we're going to follow some rules. So our goal is for our tidy rules is that we're going to have a variable one variable in each column. We're going to say that each observation forms a row, and that each type of observational unit is going to form a table. So how can we do that using Pandas? So we're going to start by importing our data, importing the libraries, and we're going to read an HTML table. So I want to look at basketball reference information for all the games from 2016, but that information isn't available as a CSV file or some table structure. So what I'm going to do is I'm going to take advantage of Pandas function called pd.readHTML, and I'm going to go out to that page and scrape it and bring it in. I'm then going to save it out and save it locally as a CSV file. And here's what we get. You get a data frame and a bunch of information, but notice the column names are kind of wonky. There's parentheses and forward slash and periods and stuff, and some of them are just unnamed, which isn't very good when it comes to actually trying to do real analysis. So now we have to start just cleaning up the data. And as anybody who's a data scientist, that's a lot of your job is just cleaning up information to make it usable. So we're going to leverage method chaining to do that. And this is how we're going to do it. First, we're going to remove unwanted information. We're going to take out any information we don't need. Then we're going to normalize the names and use the drop NA to take out columns and rows that have tons of null data, so it might not be valuable at all to our data. Then we're going to use the assign to make some callable Lambda function calls, set an index, and rename the axis. And the code basically works like this. So here's our column rename. I broke it out into a separate variable. And I want to create a data frame called games. Well, the games we already brought in, so I'm going to reassign it back. So we're going to use method chaining. First, we're going to rename the columns to leverage the dictionary. And then we're going to make them all lowercase. We're going to take advantage of the drop NA method. And we're going to set the threshold to 4. So anything that has more than 4 null values in it, we're going to wipe it off. Forward, take a subset of our renamed columns, because that's what we're going to use to answer a question later. Create a datetime field from the datetime value that came in with when we did the read HTML to figure out what day the games were on. Set it as an index, rename it, and sort it. And what we get is a dual index with game ID and the date, with the away team, the amount of points scored, the home team, and the home points. So now we can start answering some questions possibly. And what we're going to do is I want to know how many days of rest did each team get between each game. And I have to ask, is my data set tidy to answer my question based on the rules that we talked about before? And the hang up that we have here is that our observation, we need to make our observation in these team game pairs, and we don't have this yet. So we're going to use some code, and we're going to use pd.melt to do that. And we're going to give it the variables to get it in the format that we need. So we're going to pass in our index and the ID variables that we need. And we run it, and it's going to reshape our data frame again, and we're going to get it into that format. So we can now ask the question once again, are we tidy? And it meets the rules. So each variable is in a column. Each observation is now in its own row. And each type of observational unit is going to form our table, which is just our data frame. So now we can rethink the question like a computer scientist. So we can say how many days of rest between games to this. We can say the date of today, the game that we're looking at minus the previous date minus 1. And that'll give us the number of days rest between games. So we just basically took the problem, converted it into a math problem, and now we're going to have the computer solve it. And we're going to take advantage of our method chaining. We're going to sort by date and group by team. And then we're going to take advantage of the date different function, calculate the number of different days between the two based on the group, and subtract 1. Drop any NA values that might occur, and then we get a table that contains our rest. We can then go ahead and visualize our results if we wanted to, or do further analysis as we go on. In this case, I'm just going to show for each game, each team on the group by, I'm going to see the number of days rest between the teams as we go through. So that's just some examples of doing data wrangling. So now we're going to go on to part 3, and we're going to introduce the Spatially Enabled DataFrame. I like Pandas, if you haven't noticed. So Spatially Enabled DataFrame is built on the Pandas platform, and it has 2 special namespaces. It has one called Spatial, another called Geom. And it has a custom geometry column as well. And the reason we did that is if we didn't have it, it would be really hard to identify what actually contains geographic information, because by default, anything that Pandas doesn't understand what it is, because you can put anything into a column, it'll come back as object. And that's not very helpful when you want to keep track of what you have inside of a data frame. And the goal was to provide a different geospatial experience. And what we're able to do is we're able to load information into memory to do fast computation and on-the-fly indexing. And the other advantage of doing this is that it's multi-platform. So we can take the Spatially Enabled DataFrame and you can use it in your Linux environment or your Mac environment or a Windows environment. It doesn't matter. And it behaves the same. So you get the same experience across the board. And we didn't touch any of Pandas' underlying functionality. So we didn't use inheritance and overwrite methods to get it to work. We used custom namespaces, the accessor pattern. And on a series, so our one-dimensional array, I mentioned we used this geom namespace. So you would do df.shape, which is the default name if you were to load a feature class. And you do .geom, and then you can do geometry operations, like calculating the area for each one of the polygons if you had it in there. And it would return it back for each row, the total area. Or you can do it on the data set as a whole, so you can do things like reprojection on the fly. All in memory, so nothing ever gets written to disk. So think about what you could do. If you have a master data set that maybe it's in state plane and another projection, and you need to put it in WGS 1984 to have to make your analysis line up right, you can do it now all in memory and not have to write anything and do your analysis, and maybe you never need that WGS 1984, and you won't have the situation where you have maybe feature class 1 WGS 1984, feature class 2, is in this projection. So you don't need to create all those intermediate data sets anymore. You can do it all just in memory doing this project as. I touched on some of the other benefits, but one thing I want to point out is that it also supports multiple geometry engines. So by default, if you have ArcPy, it'll try to use the ArcPy's geometry engine. And then it goes down and it'll use Shapely. And this is especially important if you're working in non-Windows-based environments. If you have a Mac, you can install Shapely and still get your geometric operations that you need to do stuff, but it'll behave the same as if you were doing it in ArcPy and you were doing it with ArcPy on the back end. And you can also read and write data. So we take advantage of things like Fiona and PyShape and ArcPy as well to read data out to multiple formats. So you can share it with whomever you need and pass it along. So let's get started now that we know how it works and it's built. First, we're going to import Pandas, and then we're going to do from ArcGIS.features, import GeoAccessor and GeoSeries Accessor. And what we're doing is we're loading Pandas, and then we're saying, hey, Pandas, I also want to put these other 2 namespaces on there that users can use. And we can start doing data I/O operations. And we can consume multiple different types of data. So we can consume feature layers, other data frames, feature classes, GeoJSON, some OGC formats. And here's an example of doing a lot of the common ones. So let's say you have a hosted feature service layer out there, and you want to access the data and work with it in memory, and you want to get the feel of a Pandas data frame. You create a feature layer, and then you do pd.dataframe.spatial from layer, and it creates the data frame for you. It pulls the data in, it assigns the columns, and it does all this information for you. If you have local information that you want to merge, here's an example of doing a shapefile. And you do pd.dataframe.spatial from feature class. And if you have ArcPy installed, you can consume any feature class that ArcPy can read. You can put it in. So if you have an enterprise geodatabase and you're connecting through a direct connect SDE file, you just have to pass in that path and load it into a data frame or a file geodatabase, and all the other formats, geopackage, all that. You can be consumed through there. You can also make data frames out of other Pandas data frames. A very common data set that's out there is the USGS. They provide an earthquake feed. And in that feed, it's just a CSV file, but there's also lat-long values in there. So on the fly, we can make that spatially enabled and give it an actual geometry object without ever creating anything on disk. So we can do spatial.fromXY, pass in our other data frame, and just give it our XY columns. And you can even give it the spatial reference as well. The default is WGS 1984, so 4326. It's the code, but if your data is maybe a projected data set or state plane feet, you just have to declare that when you pass in your data frame. And then we can do the opposite. So we can consume, but we can also persist. So we can write to disk. We can dump it out to tables or feature classes or services. And to dump it out to a service, you can do gis.content.import data, and you just give it its data frame and the title, and on the back end, it's going to write everything up to either your enterprise or ArcGIS Online, or you can write it out to a feature class. But the other neat thing that you can do is that you can take advantage of Pandas export and import functions as well. So you can dump this out to a pickle file or HDF5 and things like that, and persist it, and maybe it's the end of the day and you don't want to have to go through all the steps you did before, so just dump it out to a pickle, and then when you come back in the morning, just load it back in to pickle, and your object just is exactly how it is when you started. So we're going to now talk about how we can work with the series now, our geometry column. And recall that a series is just a one-dimensional array of values. So we're going to start by reading a feature class. This is a polygon feature class. We're going to use the from feature class and import our data in by path. So now we have a column. We're going to look at the shape field and just show the first 5 records. When you visualize a data frame, it comes back as Esri JSON by default in the column. Let's say you want to get the centroid of all those polygons. So we're going to create a new column on the fly. So we're going to take our SDF object and call it centers. And then we're going to do sdf.shape.geom to go into our geometric operations and declare centroid. So we're going to add that on to our data, and we've declared a new one-dimensional series that contains our XY centroids for that polygon. And if you didn't want it, you could just turn around and drop it and delete it and go away. It just goes away because all this is in memory. Nothing's persist. You haven't told it to persist yet. We can also go ahead and calculate areas. So we could do area and get it as acres and summarize it all up. So the total acres for our data is 7,207 acres. So those are just some operations that you can do at the geometry level. Now let's look at some operations that we can do on the spatial level. And recall the spatial level is sort of looking at your data set as a whole. Think of it, if you were to associate it with ArcPy, the closest function I can associate it with would be the ArcPy.describe, and you're going to get information about that data set, like extents and stuff like that. But it also has the added ability of adding in reprojection. So let's take that same zoning data set that we have, load it in, and let's look at its bounding box. Let's see what we get back. It's a square. We added the ability on geometries to display SVG geometries. So you can get, not only can you get this information is actually a geometry object, but when you're in the rich environment of a Jupyter notebook, the bounding box, you can actually see what it looks like before you do anything with it. And this comes in really handy when you're doing things with geo-enrichment, just to bring it back to some other functionality of ArcGIS, because sometimes you want to know how your block looks and make sure you're covering the area that you actually want to cover. And it's a quick way and dirty way of looking at your geometry. But you can also get the full extent back as a tuple. Or we can go ahead and reproject it from our original coordinate system and put it in WGS 1984. So now we took it from this original projection, and now we have it in our new one, all on the fly. We also have rich visualizations. So on top of being able to do visualizations with plots, we can also look at it from the mapping side. So the plot method mimics matplotlib's visualization structure, and so it should be really comfortable for anyone that comes from that world. We use the Python syntax that's been adopted over time to do that, and it works on both features and attributes simultaneously, so it eliminates the need to use all these external libraries, so you don't have to. Those are all optional. So to understand renderers, you have to first know what you can do. So by default, everything's a simple renderer. That's basically just assigning colors to a circle or a square or an X and things like that. But you can also do unique, and you can even take advantage of Arcade as well to get that dynamic rendering. We also support class break and heat map rendering as well. But because renderers can be complicated, we developed helper functions for you. And they exist within the ArcPy.mapping submodule. So if you go to from ArcGIS.mapping, you can do two helper functions that I use all the time is show styles and display color maps. What show styles allows you to do is it allows you to look at various geometries and get back a table of what the syntax is for each one. And it associates back the terminology that's used when you do something in ArcGIS Pro. So for example, in O, a lowercase o is a circle, a plus is a cross, a D is a diamond, S is a square, and X is X. But in addition to that, which I think is pretty neat, is that to display color maps, what it allows you to do, because we're using the logic like matplotlib, it uses the idea of color ramps. So you can select from a whole set of predefined color ramps here to automatically assign the colors to your data. And there's quite a bit. And these are all examples of what the color schemes that you can do. So you can look before you just do. Instead of just keep adding the data and see if it looks right to you, you can possibly look at a color ramp and say, okay, this kind of narrows it down. I want this to be my lowest color, this one to be my highest color. So it's a way of judging the color map before you use it. We're now going to look at a way, I'm just going to show how you can put the data and put these in action. So what we're going to do is we're going to connect to my GIS, and we're going to load a map. And we have a map that's over top of, it's New York, New Jersey metro area. And we're going to add some data in there. And what I'm doing is I'm going to actually create a data frame directly from a hosted feature service layer. So what I did is I did a query, and I said, hey, feature layer, give me back this data frame instead of as a feature set object, which most queries come back as, just give me it directly back as a spatially enabled data frame. So we have all the data in there already. And we can go back and let's just see what the default rendering looks like. So it returns true, and we can see what happens on the back end on this map. Let me zoom in, is that the renderer decided what color to use because we didn't specify anything, and it chose the default circle symbology that you get if you were just to add points, let's say, into ArcMap. But let's see how we can go ahead and maybe customize that a little more. So we're going to take the same data set, and we're going to make it a little more, we're going to jazz it up a little. So we're going to use a simple data type, and we're going to use the square style. We're going to specify our color ramp as red, R, so it's red in reverse. So the darker colors will be in the 0 spot of the color ramp. And we're going to say we want the 10th color in our data ramp using C-step. We're then going to say I want to use this color ramp, yellow or brown, for my outline color, and then I want my marker size to be 10. So we're taking that same data set and we're adding it on, and we get a different look and feel with just a couple lines of code, and we added it on there. We can also do class break rendering as little as 3 inputs. So we're going to provide our map widget, the rendering type, and then the column we want to render on. So what we did is we took everything that's called state is going to have the same color with our unique renderer, and it adds it on there. We can also take advantage of, for class break renderers, we take advantage of the JavaScript API's rendering capabilities for the method. Here we're going to use natural breaks on our data set and plot it on the map using a numeric column for population. You can specify the number of classes you want and also the color map. And to understand what those various breaks are, new in Pandas 1.6, you get this legend capability, and it'll tell you what all these breaks are. So now you not only does it display, you also get the feel of and knowing what each color means. And all you have to do is do your map object.legend equal to true. So we showed point data, but let's see how we can maybe access some information from polygons. So I have this data set. It's a census data set. I'm going to load it in as a feature layer object, and I'm going to query it and only accept state name Washington. I'm going to reproject it on the fly to 4326 and return it back. So WGS 1984, and I'm going to return it back as a spatial data frame, and I get my data back. We can visually look at the shape and notice that it's not a point this time, it's a ring, so that rings imply polygon. And we can go ahead and we can render this data using the natural class breaks on the polygon. And now we have our polygon data set up on the map rendered based on the number of classes we selected. And then we could go ahead once again, and if we wanted to, we could show the different breakdowns of how the algorithm broke down the value spread. The next part I want to talk about is spatial indexing. And by default, the Spatially Enabled DataFrame does not include, it's basically there's no index on it on the spatial column, so you can do it on the fly. And if you don't know what a spatial index is, all it is a bunch of squares, essentially, in a tree structure, and you can quickly find locations of data based on extent. So if we were to take a data set, and we're just going to load it into a spatial enabled data frame, we can do stf.spatial, because this is a data set operation, and we can do sindex. We're going to create a quad tree in this case because quad trees build really fast, and I don't want to wait around a long time. And if I want to get all cities within the bounding box of New Jersey, I can go ahead and provide the lower left-hand side and the upper right-hand corner and select it out on the intersect. And what it's going to do is it's going to return a list of integers associated to my index on my spatial data frame. I can then take this information and use that iloc function that we learned about in the first section, and just plot the information on the map. So anything that was found within that rectangle that we created will show up on the map. But you'll notice that it's a generalized selection, so you're not going to get exact by shape. So you have to go ahead and do another step. We can take this information and just pull in the shape of New Jersey. And that's a hosted feature layer provided by New Jersey OIT operation, and it's just the official boundary for the state of New Jersey. So I can select out, just to show that we have all these other states in there, we're going to select it. I can take advantage of the geometry disjoint operation and set it equal to false because we want to find things that aren't disjoint from the polygon. Pass that in and replot the data. And if we go back up to our map anything in blue actually falls within the official boundary of the state of New Jersey. And you can see that all the stuff that was in Delaware and Pennsylvania and New York fell to the wayside. So now we could just do analysis if we were interested in the state of New Jersey. Moving beyond just doing geometric analysis, we can use in the Python API, take advantage of the spatial analysis tools that we have. So we can pass them the geoprocessing tools into a GP tool, a geoprocessing tool, and run some analysis. In this case, we're going to create a viewshed for 4 cities that are in South Charleston, West Virginia, and we're going to display the result on the map. So what we're doing is we're taking our spatially enabled data frame, putting it in a format that the geoprocessing tool wants, setting the maximum distance, and then the unit. Let's take a moment, apparently. And then we can go back and we can render that on a map. So here's our point of interest that we started with, where we did the viewshed from, and then anything in orange is what the viewshed said that we could see from that location. We can use geo-enrichment to enhance our spatial data frame to add additional properties to it. And Spatially Enabled DataFrame as a whole was designed to work well with Spatially Enabled DataFrame, so there's great interaction between those 2 modules. But we're going to pull in the enrichment functions that we need to do, we're going to do from ArcGIS.geoenrichment import enrich. And then we're going to take our spatially enabled data frame and the data collection that we want, and then enrich it. So it'll add the columns to the data set that we already had. We can visualize it on a map. And what you'll notice is that it converted, geo-enrichment has a new thing. If you pass in points, it'll buffer it automatically by 1 mile to collect the statistics and average them out for that 1 mile. So just a note. You can also do custom analysis too. So we can take, that didn't work. I'll skip that though. You can do custom analysis as well, so you can link it into other third-party modules. And what we'll do is we're going to move on to the 4th part of taking all the things we learned before and showing how we can use third-party modules and do some spatial data wrangling. And oftentimes I've been doing this for a long time, and you do a lot of analysis with things, and you look at cancer and theft and all that, and it kind of depresses you. So I found this statement, I thought it was kind of funny, by this comedian Mitch Hedberg, and it says, "La Quinta is Spanish for next to Denny's," and I wanted to know if that was actually true. So I'm going to use statistics and geospatial analysis to prove that that's true. So the first thing I wanted to do is I wanted to know if I could even find Denny's and La Quinta information. And so I'm going to declare my pandas and load my namespaces in. And lo and behold, somebody had Denny's CSV and La Quinta CSV. So apparently I'm not the only one who was interested in this association between the two. So we're going to load it in using the read CSV. And we're going to load it into just standard old data frames. And I wanted to then examine it. And luckily for me, when I used the info call, I was able to see that all of the columns were in the data type that I needed, so I really don't need to cast anything that we did before. So I don't need to leverage that as type function. So I didn't need to go back and when I reloaded it, only walk over it once and declare it. But I wanted to spatially enable it. So I'm going to use my method chaining pattern. I'm going to do pd.dataframe.spatial and then do from xy. And I just pass in and I give it my xy and the data frame, and it's going to geo-enable it. And we can take a look at it and what we have. So we have a bunch of points and all the address information for both of it. So I'm going to create my GIS object, and then I wanted to plot it on a map. And you can see just visually there's a lot of Denny's and hotels. And if we zoom in, especially in the crowded areas, you can see that these squares, which are the hotels, and the Denny's, they look kind of close. I don't, but that doesn't actually prove anything yet. So how can we take advantage of spatial statistics to do that? So I went ahead, and because I wanted to do distance analysis, I wanted to create a distance matrix. So I wanted to use, spatial indexes are good for doing that and for quickly querying your data and finding your nearest neighbor, especially R-tree indexes. Because we're in lat long, I'm going to use Haversine distance. So we're going to calculate the great circle distance between 2 points. Because I don't know if there's a La Quinta that's thousands of miles away in a straight line distance because the Earth isn't flat. Spoiler. So we're going to locate the closest La Quinta to Denny's, and we're going to, like I said, we're going to create a spatial index, find the nearest points, and save it to a list. And this is how I did it. So off of my Denny's, my restaurant, I'm going to do the spatial data frame and create an index there. I declare the type R-tree, and what R-tree is it's a third-party package that I'm bringing in, and it has some unique features where you can persist R-tree indexes on disk. So once you build your index, and if your data set doesn't change, it'll always reference the same exact loading points back into that SDF. So the next day, you can go back and use that spatial index over and over and over again, so you don't have to spend that time to reconstruct it, and you get really fast. Trees in general can get data really fast, so you get the same performance as you would with a tree data structure. So, and we're going to declare a list to hold our temporary information, and then I'm going to start walking all my rows to records, and I'm going to start using my index and taking advantage of the nearest function that our tree provides. So I pass in the lat long, and I say I only want to get the one nearest restaurant to the hotel, and I'm going to append that information after I calculate the distance back in. And that gives me the data, the data matrix, the distance matrix. So let's take a look at it after I spatially enabled it. And here we have our distance matrix. And now we can go ahead and answer the burning question on everybody's minds. Are La Quintas near Denny's? And the first thing I wanted to do is I wanted to describe my data. I wanted to see how many points I had, and I wanted to know the average and look at the breakdown of the data. But I also wanted to see if there's anything crazy on the maximum distance. So there's a couple points that might be over 1,000 miles away from a hotel. So I consider those to be outliers. So how can we take those out? But before we do that, let's just visualize some information. I'm going to take advantage of Seaborn and just look at the distribution of the counts that are less than or equal to 10 miles based on the distance and plot it out. And we can see the counts are actually pretty high. So 40%, a little more than 40% of our data is under 2 miles. So just looking at that, you probably can make the association that, there's 646 La Quintas are within 10 miles of Denny's. That's a lot. And then we can also look about how many are within 4 miles, and there's 426. So we can use what we learned in possibly high school or Statistics 101. We're going to do simple hypothesis testing to see if it's actually right. And I'm going to use SciPy and the t-stat to do this. But first, I'm going to remove my outliers. So anything that's more than 2 standard deviations away, I'm going to drop from my data set. And then I'm going to calculate the standard statistics. So I'm going to calculate my t statistics, my t critical, and my p-value. And you'll notice right here that they are close because p is super, super small. It's basically 0 at the 95%. So we're going to recall our null and alternative hypothesis, look at our test statistic. Our p-value is basically 0. And because our t-value is greater than our t-critical, we're going to reject our null, or we can also reject because our p-value is less than 0.05. And this means that we've proved that Mitch Hedberg's observation was correct, and Denny's appear to be close to La Quintas. So that wraps it up for what I have. I hope you enjoyed it. I'm going to take some questions. Let me go back to this. And I really appreciate you taking the time and having some fun with me. All right, let's open it up. Thank you. Okay, yeah, I forgot to do that. On github.com/Esri in the Python API repo, there will be a talk folder, and all talks, not just this one, from Dev Summit will be there. So all the code, all the data, so you can go through and reproduce that. So whether maybe you missed a session on deep learning using the Python API or anything else, it will all be there. And the other thing you can do is that there's an issue section on there where you can ask questions and report problems with the Python API. We want to hear from you. We value your feedback beyond just things going through support, because the developers, me, myself, Rohit, everybody else on the team, we read that daily. And we might not answer right away, but the first thing we try to do before we respond is figure out the answer. So we do work on it, and we really care about this product, and we love it. And we love you all for using it. So I'll open up the floor for any questions and ask away. Yes, sir.
Do you need any licenses to get spatial?
The question was, do we need any licenses to use the Spatially Enabled DataFrame? The answer is no. You can. You don't even need ArcPy to use the Spatially Enabled DataFrame. You can use it with Shapely, and that's one of the things that makes it cross-platform. So if you don't have a geometry engine, the Spatially Enabled DataFrame actually works still. You just can't do some of those fine-grained, obviously, geometric operations because there's nothing to support it. You'll get a little warning saying you can't do this. Yes, sir, in the back.
Would you be able to create a spatial data frame from a feature layer view in ArcGIS?
Yeah, so the question was, can you create a Spatially Enabled DataFrame from a feature layer view? If you can query a feature layer view, you're talking about a hosted view, right?
Yeah, sure.
Yeah, so if it's hosted and there's a query function on it, and query is enabled on that layer, then you can put it in a Spatially Enabled DataFrame. Yes, sir.
How does authentication work for
So if you wanted to persist data to a service, you would log.
how are you a unique user when you connect to a feature service, or you can only connect to public feature services?
So if you want to work with secure server, okay, the question was, how does authentication work with this? If you're going to consume data that's as a hosted layer, it takes advantage of your login credentials on the back end. So it detects whatever the active GIS is. You can either explicitly say that. So let's say you have multiple GIS objects and you're taking a service from here, there, and everywhere. You could it'll figure out which one's active, or you can specify GIS equals whatever and pass it in. I use public data here just to use public data to show you, but it definitely works with all security. And as long as your GIS authenticates your object, it'll pick up on that authentication and use whatever your connection object, your GIS class, is using at that time. So it doesn't. It's another part of the API. Yeah. Yes, sir.
When you convert to a feature collection, was that also in memory, or did that persist?
Yeah, that was in memory too, but I can persist it also if you wanted. Yep. Yes, sir. I think it was a Freudian slip. When I said ArcPy mapping, I meant ArcGIS. Anybody? Oh. Yes.
So you're constrained by putting things in memory, not performance.
So depending on what your data is and how complex your geometry is, the last time I did it, I was working daily with like 50 million point records in data set, and it was still chugging along just fine. Obviously, the more complex your data have, the more, like if you have multi-part geometries, that's going to affect performance. But overall, it works very, very well, I feel. And we've really focused on doing vectorization of functions to speed up performance on the back end. Things you won't notice, but if you were to compare it from the earlier versions to today, it's like 5 to 10 times faster than what it was. I've like racked my brains out pulling out. Any other questions? That was a good question. Thank you. Well, thank you. I'll be here to answer additional questions one-on-one and also be on the Python booth. I really appreciate you all for coming. And like I said, reach out if you need help. Try it out, and it might just change the way you do spatial analysis and analytics in the future. Thank you.